Welcome to the channel. Thanks for joining us, your one-stop destination for everything AI. If this is your first time, please consider subscribing and ringing that all notification bell. Upon reaching 1,000 subscribers, we will have exciting AI giveaways at our online store to help celebrate this special occasion. The field of robotics has reached an exciting inflection point with the rise of data-driven deep learning techniques. Recent years have seen remarkable progress in leveraging large datasets and neural network architectures to develop robotic systems capable of acquiring new skills with minimal explicit programming. However, a persistent challenge has been enabling artificial agents to transfer knowledge across different hardware configurations and environments. Approaches reliant on task-specific training rarely generalize well to novel situations. This limitation severely constrains real-world application, since recollecting demonstration data and retraining models from scratch for every new condition is not practical. Enabling robots to seamlessly adapt their behavioral policies to varied embodiments and contexts is critical for usable automation. Google DeepMind's release of OpenX embodiment represents an important step towards robotic systems capable of generalizing skills across distinct hardware configurations. The open-source repository contains over 1 million episodes capturing 22 robotic platforms across 21 institutions, representing an unprecedented diversity of embodiments and skills at this scale. Central to the project is the hypothesis that models trained on sufficiently large and varied datasets can acquire generalizable policies for robotic control. This theory aligns with similar findings in computer vision and natural language processing, where exposure to massive heterogeneous, or comparing different language varieties, yields systems with stronger transfer learning abilities. The Google DeepMind team demonstrates this by training transformer-based models, RT1 and RT2, on the OpenX embodiment data. RT1 focuses on low-level robotic manipulation, while RT2 incorporates computer vision and language grounding. Combined as RTX, the system displays substantially improved adaptation compared to prior methods specialized for particular platforms. When evaluated on common research tasks at partner institutions, RTX succeeded 50% more often on average, across 5 distinct robots. The diversity of training data leads to general principles that streamline transfer between different embodiments. Rather than needing to retrain entire models per configuration, this enables incremental acquisition of new skills. RTX also exhibited capabilities beyond the constituent skills in its training distribution. When evaluated with new objects and predicates, it generalized more robustly than prior work. For example, RTX could accurately place an apple near a cloth versus on top, using only the prepositional knowledge, without explicit training. This demonstrates how broad data equips models with richer conceptual representations. The researchers posit that subsequent self-supervised learning could allow such agents to continuously expand their implicit understanding of how the world behaves in various contexts. Gathering robotics datasets substantial enough to yield these generalization benefits has posed a persistent obstacle. Most prior efforts concentrated on specific skills, environments, and platforms. In contrast, the Internet provides a natural source of abundant visually and linguistically diverse data for computer vision and natural language processing. Simulating robotic interactions has also proven challenging, given the complexity of simulating dynamics like friction and deformation. While graphics and physics engines constantly improve, bridging the reality gap to real-world application remains an active research problem. Collaborating with dozens of academic labs enabled the assembly of a uniquely large and wide-ranging robotics dataset. Reducing barriers to entry will empower more researchers to build upon these initial results and investigate what mixtures of data are most valuable. The overarching motivation is advancing robotics in an open, responsible, and ethical manner. Broadly generalizable agents could significantly improve the usefulness of robotic systems. However, real-world deployment involves addressing complex issues like transparency, accountability, and safety at scale. Initiatives like OpenX Embodiment exemplifies how a like-minded community can collectively steer progress, with inclusive platforms and incremental benchmarks. While cross-embodiment learning shows promise, transferring these capabilities outside of controlled environments demands much more research. There are also open questions regarding how architectural choices impact emergent behaviors as scale increases. Larger models trained on more diverse data acquire nuanced understandings of how the world behaves in various contexts. However, these implicit mental models become difficult to interpret and analyze. Understanding how particular training curricula yield certain inductive biases is an active area of investigation. For example, a model trained heavily on kitchen environments develops an intuitive physics model that extrapolates poorly to driving scenarios with momentum and friction. Analyzing correlations between training distributions and emergent capabilities will help to instill safe, controllable, and beneficial attitudes. As models grow more capable, we must better comprehend their internal reasoning to ensure alignment with human values. Simultaneously, we must recognize the limitations of existing methods. The skills encompassed even by large datasets, like OpenX Embodiment, capture only a minute fraction of human ability and common-sense reasoning. To achieve more human-like versatility, robotic systems must continue scaling up significantly across numerous dimensions. This includes expanding the diversity of training data, increasing model capacity, and incorporating additional modalities like audio, haptics, and proprioception. For instance, a robot trained exclusively on visual inputs will struggle to learn skills like using a whisk, which relies heavily on tactile feedback. Architectures must also better integrate world knowledge and physics models with end-to-end training. Combining simulation and physical data can help expose models to an exponentially greater variety of situations and skills. But efficiently transferring from simulation to reality remains an active challenge. For example, capturing the dexterity and force control needed for surgery would require profoundly high-fidelity simulation of tissue deformation, sensing, and actuation. OpenX Embodiment represents exciting progress. Developing trustworthy autonomous robots that can operate independently in ambiguous, complex situations and learn continuously, like people, can be seen on the horizon. More incremental milestones must first be met across areas like standardized benchmarks, simulation techniques, model interpretability, and data sharing. Open-source initiatives can help align the development and assessment of increasingly capable machine learning-driven automation with ethical principles. In the near term, we may witness a proliferation of robotic systems that can adapt to moderately varied tasks across several environments while operating within strict safety boundaries. But researchers stress that near-human versatility requires more data, computes, and algorithmic innovations. Furthermore, accurately evaluating the general competence of systems remains an open problem. Existing benchmarks measure narrow skills under idealized conditions. Truly assessing robots outside these constrained settings demands nuanced, multifaceted tests, grounded in real human needs and activities. Looking ahead, multi-institute collaborations on open datasets and models appear critical for responsibly steering progress. By pooling resources and distributing benefits inclusively, the robotics community can collectively determine how best to deploy these technologies for human betterment. The choices made today in how autonomous systems are developed, validated, and governed will shape their evolution and real-world integration for decades to come. Initiatives like OpenX Embodiment demonstrate how shared platforms can enable ethical, transparent, and accelerated innovation towards useful applications of artificial intelligence. In conclusion, the OpenX Embodiment project pioneers a collaborative approach to instilling robotic systems with greater generality and transfer learning abilities. By pooling data across research institutions and sharing open-source tools, Google DeepMind aims to spur responsible innovation towards adaptable autonomous agents. The initial results demonstrate that enormous variability is key. Models trained on broader data develop more flexible policies applicable across platforms. This aligns with similar findings in computer vision and natural language processing that highlight the benefits of scale and diversity. Initiatives like OpenX Embodiment can help align the development of increasingly capable automation with ethics principles through incremental benchmarks and inclusive platforms. Near-human versatility likely requires more data, compute and algorithmic advances. Progress will involve executing expanded data collection, developing physics-grounded simulators, increasing model scale, and designing comprehensive benchmarks. Multi-institute collaboration around open datasets and models appears critical for steering robotics down a responsible path. By transparently building upon these initial achievements, researchers can unlock the full societal potential of robotic automation. Okay, that is the current update on Google RT2X. Go ahead and share your thoughts in the comments. Don't forget to click the notification bell so you never miss out on the newest updates in the world of AI. We are highly interested in your feedback and how we can improve or bring additional topics of high interest. Remember, every like, comment, and share brings us closer together as a community. Until next time, stay curious, stay passionate, and most importantly, stay awesome. Thank you for watching, and we will see you in the next video. This is Make Money AI signing off.